Our last speaker of the morning is Charles Walker, who's going to tell us about no-iteration pseudo-distributive laws. Please go ahead.
Right. First, I want to thank the organizers for setting up the conference and for giving me an opportunity to talk here today. Right, so I'll start off just by reminding you about the definitions of pseudomonads in both their monoidal and extensive forms, and the coherence axioms that these are meant to satisfy, which will be important in this talk. Then I'll remind you about what's known about pseudo-distributive laws up until now. Then in this second section of the talk, I'll tell you a bunch of different presentations of pseudo-distributive laws. I'll give one based on the usual monoidal presentation, a version which involves some decagon axioms, which I'll talk about a bit later. Then I'll use these decagon axioms to explain why 3 of the usual coherence axioms for pseudo-distributive laws are redundant. And then I'll also give a presentation of pseudo-distributive laws in terms of a pseudo-algebra structure maps and a no-iteration version of pseudo-distributive laws. And if I have time at the end, then I'll also say a bit about what happens in the case when one or both of these pseudomonads are KZ or like-sided impostent. Right, so a pseudomonad in monoidal form, just a pseudo-endofunctor on a 2-category C with pseudo-natural transformations U and M. Right, and the 2 triangles and the square might only commute up to some invertible modification. Right, and these modifications are meant to satisfy some coherence axioms. Right, so the first axiom is just some axiom involving 2 units and an associator here. So just think of this as some analog of the triangle equation. And this other one involves 5 copies of the associator, right? So some version of the pentagon equation. Right, and so by results of Kelly and McLean, it's well known that there's 3 useful consequences of these axioms, which are these 2 axioms and so this one here. Right, and so there's also the extensive presentation of a pseudomonad on a 2-category C. And so this is defined by giving an assignation on objects, sending each object X and C to another object Tx and C. For each object X, we're meant to give a map from X to Tx. And for each pair of objects X and Y, we're meant to give a functor taking maps from X to Ty to maps Tx to Ty. And usually this functor is called the extension operator of your pseudomonad. Right, and we're also meant to give some left unit law data here, which is isomorphisms inside these triangles, making sure that any f x to ty is isomorphic to the unit followed by the extension of f. We're meant to give some right unit law data, which is just an isomorphism which makes sure that the extension of the unit along itself is isomorphic to the identity. And we're meant to give some associativity law data, which just ensures that extensions are preserved by other extensions, at least up to some isomorphism. Right, and as before, this is meant to satisfy 2 coherence axioms. So here we have some unit law data, some other unit law data, and the associator here, right? So again, we have just some version of the triangle equation. And the other axiom is just an analog of the pentagon equation, right? But now expressed in this extensive form, but analogous to earlier, right? in the same way as earlier, we also have these three consequences of the triangle and pentagon equations, which are these three conditions here. All right, and it was shown by Marmolejo and Wood that pseudomonads in monoidal and extensive form are in equivalence. All right, so why do we need pseudo-distributive laws? Well, even when you're dealing with just two monads, you often have to use the pseudo version of distributive laws. So an example of this is when T is the two monad for small symmetric monoidal categories, and P is the two monad for small categories with finite products. And in this case, there's no strict distributive law TP to TP, because if you work it out, one of the pentagons won't commute strictly, but it will commute up to an isomorphism. Right, so in this case, we have a pseudo-distributive law, but not a strict distributive law. Right, so we must allow these required diagrams to only commute up to some invertible modifications satisfying some coherence axioms. Actually, in working out these coherence axioms, that's the complicated part, right, for a pseudo-distributive law. Right, so let's give some history. I guess that Kelly was the first to consider these pseudo-distributive laws. So he considered the case where both triangles and one of the pentagons commuted strictly, and he arrived at, say, 5 axioms with these so-called semi-strict pseudo-distributive laws. And Marmolejo considered the general case, requiring these 4 modifications to satisfy 9 coherence axioms. And in Tanaka's thesis, she introduced an extra 10th coherence axiom. Right, then after that, so Marmolejo and Wood showed that Tanaka's extra 10th axiom, in addition to one of the original 9 he had, are redundant. I've shown that 8 axioms suffice. Right, and so today we'll show why 5 coherence axioms suffice. So of course we won't have time for all the details. Right, so what are these 5 coherence axioms? Right, so this is what I'm going to call a pseudo-distributive law, just in the usual monoidal form. So 4 modifications in the 2 triangles and the 2 pentagons, and the 5 coherence axioms that we need. Some axiom involving one of the triangles and one of the pentagons, an axiom involving the other triangle and the other pentagon, an axiom involving associativity of one of the pentagons, right, and associativity of the other pentagon. Right, and so far I've just given you the axioms for a pseudomonad morphism and opmorphism. We also need this 5th axiom, which is just an interchange rule between the 2 pentagons. So requiring that this pacing with, say, omega-4 on top and omega-3 on the bottom is equal to this pacing with the omega-3 on top and the omega-4 on the bottom. Right, and so this is the best you might hope for in that this means you only need a single coherence axiom to ensure that the opmorphism is compatible with the morphism data. Right, so the way that we'll prove that these 5 axioms suffice is by extending to the Kleisli bicategory and using the fact that pseudo-distributive laws are in equivalence with extensions to the Kleisli bicategory. Right, so here we're taking a Kleisli morphism from X to Y in the Kleisli of a pseudomonad P, just to be a morphism X to PY. Right, so if you're given a lambda, so just the basic data for a pseudo-distributive law, you would hope to define a pseudomonad on the Kleisli by sending a morphism, so F X to PY to this. Right, and so if you work out what do you need to make sure that this lambda actually gives you an extension to the Kleisli, with this extended monad presented in the usual monoidal form, then you arrive at these usual, say, 4 axioms involving the two triangles and the 2 pentagons. But if you work out what's needed to extend the pseudo-monotopic Kleisley with the extension presented in extensive form, then you arrive at 3 axioms for a distributive law. And so these 3 axioms will correspond to this left unit law, the right unit law, and the associativity law. Right, so what do these 3 axioms look like? Right, so instead of giving 2 triangles and 2 pentagons, in this case we give 2 triangles and a decagon. Right, so at first this might look a bit strange, but that's only because we're taking a lambda as the basic data here. So when you write this in terms of pasting off rays, it looks a lot more natural, and that's later on in the talk. Right, and this data is meant to satisfy some coherence axioms. This looks complicated, but this is just some version of the triangle equation. Right, and then we also have some version of the pentagon equation, which is the equality of this and this one. Right, so you can think of this decagon as the 2 pentagons combined into a single coherence axiom. Right, and so this is because, so from the pentagon, the decagon is constructed just as this pasting diagram. And conversely, if you're given a decagon, you can just restrict along units and simplify to recover one of the pentagons. And you can restrict along, say, other units and simplify to recover the other pentagon. All right, so let's recall these 3 redundant coherence axioms for a pseudo-monad presented in extensive form. All right, so if we look at this first axiom, right, so this says some unit law data composed with another unit law data is going to give us an identity. And remember that the unit laws are corresponding to the triangles here, and the associator is meant to be this decagon condition. So you can probably see that there's 2 unit laws composing to the identity. It's just going to correspond to this coherence axiom here. All right, this explains why this axiom is redundant. And you can also prove that this coherence axiom follows from, so this redundant axiom, and dually that this axiom follows from, so this redundant axiom. All right, so there's also some other presentations that I wanted to mention of pseudo-distributive laws. Right, so this one, instead of giving a lambda from TP to PT, we're going to take our data as a transformation from TPT to PT. And this is going to be equipped with 3 modifications. So in a triangle, in the square, and the hexagon is below. And so actually the decagon from earlier has collapsed into a hexagon here. And again, we have some version of the triangle equation and some version of the pentagon equation. So this is meant to satisfy. Now I mentioned here that it turns out that this map alpha gets a pseudo-algebra structure just for free as a consequence of these axioms. And so that's why you might call this the kind of pseudo-algebra presentation. All right, then I also mentioned here that you can replace, so this data here by this square here by this square here. So what's going on here? Well, if T is in monoidal form, then it's natural to consider this axiom where we have a multiplication map. But if you're thinking of the monad T as being in extensive form, then you're not given the multiplication as part of the data. And so in that case, it'd be more natural to just use this second axiom, satisfying an analogous coherence axiom. Right, and so this ultimately leads to the definition of a pseudo-distributive law in no iteration form. Right, and so this will just be a two pasting operator, which is a family of functors taking maps x to pty to maps from tx to pty, satisfying a couple of axioms called whiskering and blistering, but we won't worry about that here. Right, and we're also meant to give a fat family of cells in each of these three triangles here. Right, and as we'd expect, we have some version of the triangle equation that this is meant to satisfy, as well as some version of the pentagon equation, now stated in terms of these pasting operators. Right, so this is equal to pasting. Let me just mention that if you wanted to avoid iteration of both the pseudomonads, then instead of this triangle here, right, you would use just this cell here. Right, this corresponds to the choice you had earlier, satisfying some analogous coherence axioms. Right, so maybe I'll just say a bit about what happens when one or both of them are KZ pseudomonads. Right, so for considering a pseudo-distributive law in the case where the pseudomonad P with unit eta is KZ, it's useful to use the op algebra presentation. So the usual form, which is just the usual lambda, does have some nice properties. So for example, in these triangles, the lambda will just be a left extension. If we use the op algebra form, then the data will be a P homomorphism, which I'm calling res T eta at the moment. I'll explain it in a second, which is a map from PTP to PT. And this is going to be the right clariflexion adjoint to PT of the unit. Right, and it's just nicer to use adjoints than extensions because this lets us prove coherence axioms just using the mates correspondence. Right, so why do I call this res of say T of the unit? Well, it's because when P is the small co-completion monad, then this res T eta is just restriction by T of the unit. Right, the right adjoint of LAN of T of the unit. And also this approach has a nice interpretation, namely that there's a fully faithful functor from say monads in cat to double categories, which sends a monad to the double category of what you might call as P-split monos, or I like to call them P embeddings. And these are pairs of maps and L from A to B, and the res L from PB to PA, such that PL res L is the identity, and res L is a P homomorphism. Right, and this sort of embedding can be generalized to the case of KZ pseudomonads, basically just by taking this PL res L to be a co-reflection adjunction. Right, so I want to use this op algebra form to explain a result I proved a couple of years ago. Right, so a while ago I showed that pseudo-distributive laws in the case when P is a KZ monad amount to just giving modifications in the two triangles and one of the pentagons, satisfying these three coherence axioms. Right, so an axiom involving a KZ structure cell, an interchange of the units of the triangles, and an axiom involving one of the pentagons, or the only pentagon. Okay. Right, so what's going on with these three coherence axioms? Well, the KZ looking axiom is just what ensures that we have this co-reflection adjunction between PT of the unit and our data for our distributive law, which is our algebra structure map, res of T eta. And the last two axioms, they just ensure that the triangle, which becomes a square in the off algebra form, is just the mate of some naturality square. Right, and also the pentagon, which becomes a square in this algebra form, is related by mates to this naturality square. Right, and the rest of the coherence axioms, in this case, also just follows straight from the mates correspondence. Right, and this also gives you uniqueness when one of them is kz, right? Because that adjoint's unique up to unique isomorphism. And the rest of the data, those two modifications, are just related by the mates correspondence. Right, so it's unique when one of them is kz. Right, and so maybe I'll just finish by mentioning the case where T is a co-kz monad and P is a kz monad. Right, so what happens in this sort of setting? Right, so in this case, a pseudo-distributive law will just be two modifications in the two triangles, satisfying any two of the following three coherence axioms. Right, so we have two axioms involving the two different structure cells of the kz pseudomonads. Right, and this axiom about interchanging the two triangles. It turns out that of these three axioms, any two will imply the third. Right, and this also generalizes to any mix of kz and co-kz monads, provided you use the appropriate analogous axiom involving the kz structure cells. Right, so these are the references. And thank you.
Thanks. We have time for questions, but before that, let me say that there will be an announcement after the questions. So let's go ahead with the questions or comments. Steve, you have a question.
Hi, Charles. Good to see you, and thanks for that. Very nice. I just wanted to mention there's sorry, I'll put my video on. Sorry, I didn't notice that. Hi, Charles.
Hi.
There's Ross Street and I have a paper called On Monads and Warping. I don't know if you know about it, but we also noticed that those three axioms were redundant and had, had perhaps in some way a similar approach involving Kleisel extensions and so on. Although we certainly didn't do all of the same things you did.
Okay, well, thank you.
Sure.
Paul.
Last time I did something with horrendously big diagrams. I was told off by a junior categoryist, specifically Jamie Vickery. Amongst the younger generation of categorists, it's people like using string diagrams. I wonder whether what you're doing might be easier with string diagrams. Did you look into doing that?
Yes, so that's a good question. I haven't tried expressing all this in terms of string diagrams yet. Yeah, I am curious what that would look like.
Any other question or comment? What? Then let's thank the speaker again.